which relates the rank of the matrix, A, and the rank of its Jordan normal form. And it shouldn't be surprising that the ranks of these two things are really closely related, because they're basically the same transformation, but just with a change of basis applied, right? And so what we're going to do is let's consider J given by this change of basis here. A is some matrix, and if you know the change of basis that you need, then conjugating with that change of basis matrix, you can end up with the Jordan form. And whenever you conjugate by invertible matrix, it doesn't change the rank. So automatically A and J have to have the same rank, because if you conjugate this, the rank of what you get is going to be the same as what we had for A. So that's, you know, a little preliminary comment there. Let's consider this matrix here, though. This pair of matrices, rather. These two matrices are going to have the same rank. And to see that, we'll use that previous comment that I made, that if you have a change of basis, P inverse AP, the rank of A is going to be the same as the rank of the new matrix that it's transformed into. Okay, so let's go ahead and justify this theorem by noting that J minus lambda I can be thought of as, we know J is P inverse AP, so J can be thought of as P inverse AP minus lambda I. This matrix here secretly has two copies of P, you know, this P inverse and P. It has those items hiding right here. So let's rewrite this term with that P inverse and P written explicitly in there. Okay. Because if you multiply these matrices together, you certainly still get the identity. All right, so we can rewrite that term with a P inverse and P showing explicitly. And then what we can do is factor out P inverse on the left and factor out P on the right. And so this matrix right here has to have the same rank as that matrix there, because what we did is we took this matrix and conjugated it by an invertible matrix, which we discussed in that previous line. Conjugating by an invertible matrix doesn't change the rank of this matrix. So what that says is rank this is equal to the rank of this which we know is equal to the rank of the original matrix A minus lambda I. Okay. So that's an extremely important fact that we're going to use repeatedly. But we actually need a slightly stronger form of this. We not only need to verify that this matrix has the same rank as this matrix, but in fact all powers of this have the same rank as all powers of this. And so we'll introduce this little corollary here. Corollary is just something that follows immediately from something else. As a corollary to this previous theorem that we just proved, we can verify that the rank of all powers of this matrix are the same as the rank of all powers of this matrix. And so to see this, it's pretty easy. All we have to do is same sort of deal as before. And let me take a look at how I set this up in my notes, because it's yeah. So we know that this thing raised to the power k can be thought of, we know that this in matrix can be thought of as P inverse A minus lambda I P. Okay. Because we know that this thing can be written as a change of basis applied to that matrix there. And now what we'll do is we'll write this out. We'll write out k copies of this, okay? So there's one copy. Second copy. And so we just write out k copies. And in doing that, we notice that the inner product here, P times P inverse, this product here reduces out of the picture. This just drops down to an identity matrix. And that's going to happen for all of these inner pairs, right? So for these two adjacent pairs, those middle terms drop out to the identity. For these next pairs, those middle terms, P and P inverse, drop out to the identity. And so inside, since all those P and P inverse terms drop out, all that we have left is there's one copy of A minus lambda I. There's another copy of A minus lambda I. And so all that we get is we get P inverse that's left on the outside, k copies of A minus lambda I. So A minus lambda I to the k, and then P that's left from this term on the very outside there. And so that says that j minus lambda I to the k is really just this change of basis here, where you take A minus lambda I to the k and change the basis using that same matrix P. And then, if this matrix is equal to that matrix, then certainly the ranks are the same. And we know that in multiplying, in changing basis, multiplying with an invertible matrix in this way doesn't change the rank of this matrix here. And so we get that. The rank of this matrix matches the rank of that matrix. So not only do A and J have the same rank, but A minus lambda I and J minus lambda I have the same rank, and all powers of A minus lambda I and all powers of J minus lambda I have the same rank as well. Okay. Okay, good. So this is sort of the main tool that we use in setting up the Jordan normal form. And we basically use it as a probe. And that's not really going to be that clear until we work through this example here. But we're going to use this as a probe because when we Well, never mind. Let me just keep going here, and we'll see what I mean by that whole probe comment in a couple minutes. So let's consider this matrix A then. This matrix A, suppose we want to put this thing into Jordan normal form. Then, since the Jordan normal form has those eigenvalues front and center, right, because each Jordan block is J sub lambda. So the Jordan block has those eigenvalues front and center, and we obviously have to track those down if we want to compute the Jordan form, right? So for the eigenvalues, we know we compute the characteristic polynomial, which says take determinant lambda I minus A. And when you do that, you'd end up with this lovely polynomial here. It's going to equal x to the 7th minus 19x to the 6th plus 154 x to the 5th plus 690 x to the 4th plus 1845 x to the 3rd minus 2943 x squared plus 2592x and minus 972. Okay. So to compute eigenvalues, I guess I should have an x here, since we've got an x here. To compute eigenvalues, compute the characteristic polynomial, set it equal to 0, and you solve. And it turns out this characteristic polynomial can really be rewritten as x minus 3 to the 5th, x minus 2 to the 2nd. So those are the two eigenvalues that we're going to see in the Jordan blocks. And this is our goal. This is where we want to head. This is where we want to end up. And we can see exactly that. We've got 5 copies of 3 in the Jordan normal form and 2 copies of 2. So you can see that comes out in the characteristic polynomial. Okay. But you'll notice that just knowing these eigenvalues is not enough, because that doesn't tell us anything about what the Jordan normal form might look like. For example, just looking at that, we may have a Jordan normal form that had, say, 3, 1, 0, 3, and then 0, 0, 3, and then 0, 0, 0, 3, 1. So just knowing the eigenvalues doesn't give us that much information about the Jordan normal form, because we notice that this also satisfies that same feature, that we have 5 copies of 3, 2 copies of 2, right? We notice we have this 2 by 2 Jordan block here, a 1 by 1 Jordan block here, another 2 by 2, and then a 2 by 2 with 2's, right? So this is just very, very preliminary. We still have a lot of work to do to figure out what shape, what size do all those Jordan blocks have, right? And so, what we're going to do is, let's do a little side calculation to help build intuition about how we're going to use that probe of looking at ranks of things. And let's consider this Jordan block here. I chose a different number just to make sure it doesn't get mixed up with what we're doing with this matrix. So this is a completely unrelated matrix here to what we're doing. let's consider this Jordan block here. And let's take a look at how the rank of this behaves when we consider J minus lambda I, where lambda is at eigenvalue 5. When we consider this matrix, what we get is, I'll write it out step by step so we can see it. J minus this diagonal matrix here. And what ends up happening is you just get the diagonal of this thing is going to drop, and you'll just have ones. On that upper diagonal there. And so here's the key feature to notice. This original Jordan block had rank 3. And when we plug in minus 5i, that eigenvector associated to this column right here, when you compute that difference, J5 minus 5i, that term drops out, right? And so now you'll notice that the rank of this matrix is 1 less than the original J. And so that right there is the key to help us determine how many Jordan blocks is our matrix A going to have. For each eigenvalue. Okay. I'm glad we have these two Jordan forms written here. In this particular Jordan form, suppose that we calculated that J minus lambda I. Then what would happen? This whole diagonal would switch to zeros because we'd have 3 minus 3 running along that diagonal, and this diagonal would switch to negative 1, so we're subtracting 3 along the diagonal. So what would happen to the rank? I won't write it out. What would happen to the rank? That term would drop to 0, which means that this was originally a pivot in the J. But when we consider J minus 3i, it's no longer a pivot column. And so the rank has dropped by 1 because that term dropped to 0. Same thing here. This is a pivot in the J, but when we consider J minus 3i, that drops to 0, so we lose a pivot there. This is a pivot in J, and J minus 3i, that drops to 0, so we lose a pivot there. But all the rest of these things would stay, right? And so this term here, we'd lose a pivot there, there, and there. And that drop in rank of is originally rank 7. And when you consider J minus 3i, it drops by a rank of 3, is telling you that that 3 was an eigenvector in 3 separate Jordan blocks. Okay? So this thing, for this particular matrix, the rank drops by 3. And therefore, there's 3 Jordan blocks. With eigenvalue 3. Okay? This is secretly where we're headed with A. And so in this particular example, we notice that if we consider j minus 3i, this diagonal is just going to decrease by 3. So we get 0 here, 0 here. And so we lose a pivot here, and we lose a pivot here, which means that the rank drops by 2. And so that tells us that we have 2 Jordan blocks with the eigenvalue 3. Okay. So that's all happening in the Jordan form. We're looking at these Jordan forms and we're saying, oh yeah, when we have the Jordan form in front of us, we can easily see that when you take j minus that eigenvalue, the rank is going to drop by however many Jordan blocks you have. But when we're looking at some arbitrary matrix A and we don't know its Jordan normal form, how do we determine that the Jordan form is going to have 3 Jordan blocks, or in this case 2 Jordan blocks? We just compute A minus lambda I and compute its rank. And since the rank of A minus lambda I matches the rank of J minus lambda I, then by computing the rank of A minus lambda I and computing how its rank drops, we then identify that in the Jordan normal form, the rank is going to drop by a similar amount, and therefore, using the rank of A minus lambda I, we can determine the number of Jordan blocks in J. Okay. So, let's take a look at A minus 3i. So first of all, secretly, this is what would happen in the Jordan form if we took j minus 3i. All the 3's down the diagonal switch to 0s, and then the 2's that were here would switch to -1. And we can see that rank drop that we lost a pivot here, and we lost a pivot here. Okay? What it looks like in A minus 3i looks very different, and we have some work to do. Okay? In A minus 3i, we get this new matrix here, and then what we have to do is we have to compute its rank. Okay? So to do that, obviously we have to do some row operations, which we won't spend much time on. So we just do normal row operations. And we see that A minus 3i, if you take negative row 5 plus row 4, those rows are going to add to 0. And so we can clearly see that the rank has dropped by at least 2, because we have 2 rows that are nothing but zeros. So we know the rank is dropped by at least 2, so there are at least 2 Jordan blocks that we're going to find. And now, let's keep going and put this into a more reduced form. And so we'll swap row 2 and row 1. That gives us that. Negative row 2 plus row 1, and then swap some rows around. And we put it into this form here, in which we can clearly see that in this matrix we have 5 pivots. We have this pivot, that one, that one, that one, and that one. And this thing is, close to being lower triangular. It's not. Sorry, it is. It's lower triangular. We've got these pivots showing, so we see that okay, the rank has dropped by at least 2 because we have 2 rows of zeros, and all of these pivots here would stick around if we reduce this completely. So those 5 pivots then tells us that the rank for the original matrix A was 7, and in A minus lambda I, it dropped down to 5. Okay? So since the rank dropped by 2, that tells us that the Jordan form has 2 Jordan blocks with eigenvalue 3. Okay. So that's the first way that we've used this rank as a probe to determine the structure of the Jordan form, is that it tells us that we have 2 Jordan blocks with eigenvalue 3. But we don't know how large those Jordan blocks are, right? And so how do we determine how large those Jordan blocks are, right? Meaning, we know secretly that this is where our Jordan form is going to end up. We know that we have a 3 by 3 and a 2 by 2. But looking at A, how do we determine the size of those Jordan blocks you're going to have? And so what we do is we now start to consider powers of A minus lambda I. Okay. And so what that looks like in the Jordan form, secretly this is where we're headed. When we take powers of j minus 3i, what happens is this matrix here, when you multiply it, so first of all, this is in block form, where we have a 3 by 3 block here, a 2 by 2 block here, a 1 by 1, and a 1 by 1. And whenever a matrix is in block form like that, then taking powers of it, you just need to multiply the blocks together. Okay? So when we multiply a matrix of this form by itself, all that happens is the 1's inch up by 1 diagonal position. So if the 1's are currently here, multiply this block by itself, and they would jump up to that next diagonal position. Okay, so when we compute the Jordan normal form, sorry, that j minus 3i squared, we would end up with this, where those ones that were originally here jump up 1 diagonal position to that location. And the one that was originally here, it would also jump up 1 diagonal position. But since this guy, this 2 by 2 block, we just had a 1 in this upper corner, there's no more diagonal positions for that one to jump to, and it literally, when you take a power 0, 1, 0, 0 times itself, there's no more diagonal position for this thing to jump to, right? You multiply this out, you get 0, 0, 0, 0. And so this thing squared ends up producing 0. Okay? So the Jordan block that was here, when you squared that j minus 3i, that term drops to 0. And then, of course, we had negative 1's here, that when you square those, you'd end up with positive 1. Okay? So, that's what we know is going to happen in the Jordan form. And so what you do is, we don't know the Jordan form, so we take a minus 3i, we'd square that thing. We'd then compute the rank of it. And what's going to happen is, the rank of this Jordan form here, when we took j minus 3i, when these ones jumped up 1 position, we lost 1 more rank value. Because these things originally give you a rank of 2 for this block. When you square that, the ones jump up a diagonal position, to where now, in this 3 by 3 block, you just have rank 1. In this 2 by 2 block here, originally, this thing has rank 1, but when you square it, that Jordan block then just drops down to zeros until you lose a rank here. Okay? And so, what you do is you compute a minus 3i, you'd square it, and you'd compute its rank. You'd find that the rank of a minus 3i dropped by 2. Rank of a minus 3i squared would drop by 2, to where originally a had rank 7. When we compute a minus 3i, it dropped by 2. And then when you square it, it dropped by another 2. Okay? We knew that there were 2 Jordan blocks with eigenvalue 3. And what happened is when we squared a minus 3i, the rank dropped by 2, which means that both of those Jordan blocks had to have a diagonal of 1's above them. And so that says that each of those Jordan blocks had to have size at least 2. Okay, because each of them had to have a row of 1s that when you squared it, those 1s jumped up a diagonal position, and each one of those blocks dropped in rank by 1. And so, we're still not that much closer to finding the size of those Jordan blocks, because we now have concluded that each one had a size at least 2. Now let's compute j minus 3i cubed. We'd find that this Jordan block was already 0, so when we square, this Jordan block doesn't lose any more rank, because it's already at rank 0. This Jordan block in j minus 3i squared had rank 1, but when you cube it, now you're down to rank 0. Okay? So what happened here is when we took j minus 3i cubed, the rank dropped by 1, because that one had rank 1, this one already had rank 0. And so the rank just dropped by 1. So the rank of a minus 3i cubed is going to be started out as rank 7. The first power dropped us by rank 2. The next power dropped us by rank 2. The next power after that only dropped us by rank 1. So that says there's 2 Jordan blocks with eigenvalue 3. This one says they all have size at least 2, but when this one dropped by a rank of only 1, that said that one of those Jordan blocks has already died. It's already become 0. Therefore, that Jordan block had to have size 2. That one there says that one of those Jordan blocks has already died, so we know it had to have rank 2. Size 2. Okay. So there we go. We're finally starting to nail down part of this Jordan normal form. We know that one of those Jordan blocks had eigenvalue 3, and it had size 2. Okay. Let's take another power. So j minus, sorry, I don't think I did this in the notes here, but j minus 3i to the 4th, you'd just be taking this thing and multiplying by another factor of j minus 3i, and you just end up with plus 1 here. All the rest of this stuff would remain the same. So the rank would drop again by 1. Started out at 7, dropped by 2 because we have 2 eigenvalues, 2 Jordan blocks, dropped by 2 because they each had size at least 2, dropped by 1 because one of them had already died, and then if you take a 4th power, it would drop by another 1. Wait a second, let me see. Oh, no. Yeah, the rank of this wouldn't change. Sorry. The rank of this wouldn't change because on the previous guy, j minus 3i to the 3rd, we already have all the Jordan blocks with eigenvalue 3 have died. So when you take this 4th power, the rank wouldn't change and it would still just be 2. And that says that the larger of the 2 Jordan blocks died on that previous step, and therefore the larger those 2 Jordan blocks, had size 3. 3, 1, 0, 0, 3, 1, 0, 0, 3. And there we go. We have discovered the 2 Jordan blocks associated with that eigenvalue 3. So much work, right? It's pretty, if you want to do this by hand, it's a pretty intense procedure. And so we've now uncovered all of the all the Jordan blocks with eigenvalue 3, and we can now focus on the other eigenvalue, which was 2. And fortunately for this one, it's a lot easier. J minus 2i, what would happen is we'd be subtracting 2 from the diagonal, and each of those eigenvalues has size 2, so these terms just drop to 0. So when we did that in A, we find that the rank of this is going to take the original rank of A, and it's going to drop by 2. And that first drop by 2 says that there had to be 2 Jordan blocks. With eigenvalue 2. Okay. Fortunately, once we consider the next power, j minus 2i, and we square it, the rank doesn't change. It's still going to be rank 5. And what that says is that the size of those Jordan blocks had to be 1, because the diagonals of 1s that appear above the eigenvalues those diagonals of 1s that appear above the eigenvalues, those are the things that determine power, how much the rank is going to drop when you take powers of this thing. And so what that says is that if you take j minus 2i and you get an initial rank drop of 2, that says you have 2 Jordan blocks. But then if you take another power of that and you get that the rank hasn't changed, that says that there weren't any diagonals of 1s above to make that rank drop. Therefore, we see that since this thing, the rank didn't drop anymore, that says there were no diagonals of 1s, and therefore each Jordan block had size 1. And we could have determined that already, in the sense that we've accounted for 2 dimensions in this Jordan block, 3 dimensions in that Jordan block, for a total of 5. And from this calculation here, we already see that we have 2 Jordan blocks with eigenvalue 2. And since they have to make up the other 2 dimensions in our matrix, then we see automatically that each one of them has to have size 1. But, assuming that we hadn't noticed that, or that we were doing a more part of a larger calculation, this is how you determine that each of those Jordan blocks had size 1. And so we have completed the Jordan normal form. We see that the Jordan normal form for A is we have a 3 by 3 with eigenvalue 3. We have a 2 by 2 with eigenvalue 3. And then we have 2 1 by 1s with eigenvalue 2. I think this is the craziest I've ever filled in the matrix. But there's our Jordan blocks for the eigenvalue 2, Jordan block there. So, any questions? And then, of course, we all know what we would secretly do if we wanted to calculate the Jordan form is we'd go to Wolfram alpha and we'd type it in there. So I did this earlier and I had the text copy-pasted and then I forgot to email it to myself. But anyway, you type it in there and just tell it compute the Jordan form and it would give you that without doing any work. So, yeah. So this is what we use to exponentiate matrices. This is about as clean as you're going to get a matrix to look. And then by rearranging this in a very simple way, you can then start to exponentiate matrices using literally just basic algebra. It's all like the matrix exponentiation, once you get into this form, literally requires about 5 or 6 steps and you're done.